This presentation will discuss the basics of Tensar TriAx Geogrid, including product information and performance mechanisms. We'll start by describing Tensar's manufacturing process and the characteristics of biaxial and triax geogrids. Then we'll discuss the performance mechanisms of geogrid in roads as developed by the U.S. Army Corps of Engineers. Tensar's manufacturing process for geogrid is a three-step process known as extruded, punched, and drawn. In the first step, raw polymer is melted and extruded into a sheet. The second step consists of punching a series of holes in the sheet in a precise configuration. These holes will become the apertures of the geogrid. In the third step, the punched sheet is heated and then stretched, first in the machine direction along the roll, and then in the transverse direction across the roll. This process opens the holes in the sheet into the geogrid apertures and gives the product its strength and stability by orienting the polymer molecules in the material. The finished product is rolled and taped, checked for quality control parameters, and placed into inventory. Tensar's original geogrid product, biaxial geogrid, has ribs in two directions and rectangular or square openings. This product was introduced in the late 70s. Tensar continues to manufacture biaxial geogrid for multiple uses, and several competitors now manufacture their own versions of this product. Tensar TriAx Geogrid was introduced in 2007 after many years of research and development to improve on the performance of biaxial geogrids. TriAx Geogrid has ribs in three directions, resulting in triangular apertures and a hexagonal structure. TriAx also has a rib shape that is different than biaxial geogrids, with the height of the rib greater than the width of the rib. This improves the ability of TriAx to confine aggregate particles and also increases the flexural stiffness of the material. The various aspects of the TriAx geometry result in improved confinement of aggregate, greater stiffness in the stabilized layer, and better distribution of applied loads. This allows TriAx designs to use less material, get built faster, and last longer than biaxial geogrid designs. Now let's discuss how geogrid works. The U.S. Army Corps of Engineers has identified three performance mechanisms to describe how geogrid improves the stability of granular materials in a road: the tension membrane effect, improved bearing capacity, and lateral restraint. The following diagrams from the Corps help describe each of these mechanisms. The tension membrane effect is the first mechanism identified by the Corps. This mechanism applies primarily to geotextiles used over soft soils and has limited applicability to geogrids. When tension is introduced in the plane of the material, either by stretching and anchoring it or due to rutting as shown here, it creates vertical support for the layer above. A close analogy is the surface of a trampoline. The second mechanism is improved bearing capacity. This mechanism describes the ability of geogrid to spread loads over a wider area, which reduces the pressure on the subgrade. This mechanism is analogous to the way a snowshoe allows the wearer to walk on top of snow without sinking in. In fact, it is often referred to as the snowshoe effect. The third mechanism identified by the Corps is lateral restraint. This applies specifically to geogrids and refers to the ability of the grid to confine aggregate in the grid apertures so that movement of the aggregate particles is restricted. The particles that are confined by the grid also interlock with the particles above the grid, creating greater stiffness in the layer as a whole. Lateral restraint is the most important mechanism related to geogrid performance. Now we'll look at how geogrid works under a wheel load. These pictures are from a test rig at Tensar's lab in the United Kingdom, where we can simulate field conditions to test products. We have placed a compacted gravel layer over a soft clay subgrade, and then repeated the setup, adding biaxial geogrid and TriAx geogrid. Then we load the wheel run it back and forth over the test section to simulate traffic. Here's what the gravel surface looks like after 1,000 passes of the wheel when no geogrid is used. You can see that a significant rut has developed and the material at the surface has been pushed to the side. This photo shows the results when a biaxial geogrid was added to the section on top of the soft subgrade. You can see that the rutting is reduced significantly. And here is the section using TriAx Geogrid after it was trafficked with the same loading as the other two sections. A much smaller rut and a more stable surface. But the real story is beneath the surface. This photo shows the first section, which did not include geogrid, after trafficking and with the gravel layer removed. You can see that the rut from the surface pushed all the way through to the subgrade. If this were the subgrade of a road, rutting like this would cause a failure that would require reconstruction. When biaxial geogrid is included in the section, you can see that the rutting of the subgrade is significantly reduced. This would translate into increased traffic capacity and life for the road. Now let's look at the section that included TriAx. As you can see here, the difference between TriAx and biaxial geogrid performance is dramatic. Not only was the surface rut smaller, but almost none of the rutting has come through to the subgrade. Protecting the subgrade like this has a dramatic effect on the life of the road, and it is the result of increased stiffness in the aggregate layer due to TriAx.
The performance advantage we saw in the previous slides is significant, but there are other important factors that support the successful use of geogrid. Specifically, it is critical that you have access to supporting data and expertise that make geogrid designs reliable and predictable. Since the performance of geosynthetics does not correlate to specific material properties like tensile strength, it is critical that performance be defined based on extensive testing, including full-scale in-ground tests. These tests should be conducted and/or reviewed by independent experts and should follow protocols established by recognized authorities. It is also essential that the products to be specified have been incorporated into accepted design methods. Design tools and software should follow these methods and produce results that align with full-scale testing. The chart shown here presents some of the most important aspects of performance validation and design expertise that Tensar TriAx Geogrids provide to support project success. Note in particular that Tensar has the ability to offer stamped designs if needed, a commitment to your success that is unmatched in the industry. So let's summarize what we have covered in this presentation. Tensar manufactures TriAx Geogrid and biaxial geogrids using a three-stage process known as extruded, punched, and drawn. The U.S. Army Corps of Engineers has identified three performance mechanisms for geogrids in roadway applications: the tension membrane effect, improved bearing capacity, and lateral restraint. Tensar TriAx Geogrids achieve superior performance over biaxial geogrids due to an optimized triangular hexagonal geometry and a unique high aspect ratio rib profile. Tensar provides total solution support that goes beyond product performance, with validated performance based on extensive testing and independent review, and design methodologies, tools, and support that ensure successful projects.
As always, if you need more information or assistance, please contact your Tensar Regional Manager or call 800-TENSAR-1.